Okay, get started a couple minutes early. Before we officially start, I'll mention this tomorrow, but there's another opportunity to meet prospective employees or employers. Can't talk, I guess. The name of the company is Power Engineers. So if you're looking for work in the utility industry, finding a company with the name Power is generally a good thing. But they also do more than that, right? You can see they do power and energy, which is their major bullet. They do transportation and infrastructure and earth and the environment. And Power recently got bought out, or I don't know the right term is, of this WSP. I don't know too much about it, but they have a number of offices. At least Power did. I don't know about the new company, how many offices they have, but they have a lot of offices throughout the state of Maine. Probably their major office is either Freeport or Hollowell, depending on whom you ask. But if you're looking for something, they are going to be here tomorrow from 4 to 5 in the Hill Auditorium. And again, you get free food. So it's always a good thing. And it's not just a standard pizza, right? You can get some decent Mexican food. I think it's Mexican food from Taco Vita. But the presenters, two really good guys, both alum from the EET program, and want to talk to ECEs and EETs both, and non-EETs and ECEs. And pretty much anybody who wants to do engineering, they are interested in talking to you. They will be at the job fair, but it's always good if you have an opportunity to go and meet some of the people that will perhaps be interviewing you or talking to you the next day. It's always nice to have a name and a face, and it just shows a little bit more interest when you show up and go to these things. And it's only an hour. It's a quickie one. But yeah, like I said, free food. You have to decide if your time is worth it or not. So just thought I would share that before we officially get started. But now we'll get started. So easy lab, right? Just two tiny little itsy bitsy equations that you need to solve for with some starting points, and tell me what the actual roots need to be so that you get root solving. You get f of x equal to 0. So remember what you're trying to do. These are the two equations you need to solve for x1 and x2 so that f1 of x1, x2, and f2 of x1, x2 are approximately equal, to 0, right? You can't be absolutely at 0 because, we never get the exact solution, but we want to be really, really, really darn close to doing that. So this is perfect. We have two nonlinear equations and two unknowns. This is perfect for using the Newton-Raphson's approach to do that. And if you recall, you have x of your next iteration, we'll call it n plus 1, is equal to x of the previous iteration plus your delta x. Your delta x is equal to the negative of the inverted Jacobian evaluated at that iteration result, so x of n, multiplied by your original equations that you're trying to solve for the roots, evaluated at that same x of n. Okay? And you're going to do this. So while f of x does not equal 0, or not approximately equal to 0, I don't know if that's an actual mathematical symbol or not, but while f of x does not equal 0, do Newton-Raphson, right? What is Newton-Raphson? It is find delta x, update x, and then you do your end of your while loop. Okay? So again, it's just over and over and over and over and over again. So the first thing we should do is f of x1, x2, and f2 of x1, x2 equal to 0 when x1 equals 0 and x2 equals 1, right? Correct? We're just checking that. So we can go into MATLAB. And where's MATLAB here? Whoops. That's not the MATLAB I wanted. So we've got to go ahead and solve for f1 of x1, x2, f2 of x2, and see if it's correct. So we're going to start off by calling x1 equal to 0 and x2 equal to 1. Now, here's the thing. These two functions that you're evaluating, those have sines and cosines in it, correct? And do you remember when we talked about doing Newton-Raphson? You can do it as long as you're relatively close to your guesses are relatively close to your final answers, and you're not taking these big, massive jumps. So Newton-Raphson algorithm rarely works if your calculator is in degree mode. Okay? Highlight that. Because if you're trying to use your calculator and you're in degree mode, it almost never works. You're going to get diverging results, and it's just going to drive you nuts. So in MATLAB, it's no big deal, right? Because MATLAB, it only has radian mode. So remember, if you're doing this on your calculator at home, you've got to be in radian mode. So I wanted to highlight that because I'm kind of cheating in MATLAB, right? By being in radian mode because it's only got radian mode. So now I have to write my f of x1. So 4x2 sine x2 plus x1 plus 6. So f1 is equal to 4 times x2 times the sine of x1 plus 0.6, right? That's our original equation. So step 1, that ain't 0.6, and that ain't 0, is it? That's pretty far away from 0. So I know that x1 and x2 aren't valid. The initial guesses I made aren't correct. Now, you certainly could go ahead and check to see if f2 is 0, but why bother? You already have one equation that tells me it's not a valid solution, so I'm not even going to bother checking f2. You can, but there's no reason to. It's just more work. So now I'm going to go ahead and say, all right, well, I'm stuck. I can't proceed unless I use the Newton-Raphson algorithm. So I already know my f1 and f2 equations, right? We just did this one. And my f2 equation is 4x2 squared. And then that was plus or minus 4 cosine x1 plus 0.3. Those are my two equations. The algorithm, I need f of x, and the other equations I need are my Jacobian, right? So I'm going to go ahead and specify my Jacobian in the form that it's going to be. So start off, I identify my rows. I have an F1 row and an F2 row. And my variables, X1, X2. And again, I'm being very specific in my format so that when I start multiplying and inverting, I'm going to get, the right results. I'll be able to solve for X1 and X2 properly. I'm not mixing things around. So I need the partial of F1 with respect to X1, the partial of F1 with respect to X2. This is F2. Partial of F2 with respect to X1, and the partial of F2 with respect to X2. So now I'm ready to do my partial derivatives. Partial of F1 with respect to X1. 4x2 is just a constant, right? X1 is being allowed to change, not X2. So those are constants. So 4x2 times the sine of X1 is 4x2 times the cosine of X1, right? Because the derivative of sine is cosine, and the derivative of X1 is just 1. So when I do the chain rule, I just end up with 4x2 cosine of X1. And then I take the derivative of 0.6 with respect to x1. That's a constant, so there's nothing to be done there. Now I do my partial of f1 with respect to x2, and you can do these in any order you want. This one should be pretty easy for you all. That's 4 times sine x1. Now I do the partial of f2 with respect to x1. That is going to be the derivative of 4x2 squared with respect to x1. That's constant, so that's 0. The derivative of minus 4 cosine x1 is minus 4 times the minus sine of x1, right? Which is just 4 sine x1 plus the derivative of 0.3 with respect to x1, 0. And my last one is the only thing that has an x2 in it is the first term. So that becomes 8x2. So my Jacobian matrix with actual equations in there, not numbers, but equations. And I'm doing this with equations because I'm trying to show you the process. When you calculate it out, you have to actually have you're actually going to have numbers in there. But I'm setting it up so that hopefully you'll see where the equations come from or where the numbers come from. 4x2 cosine x1. This is 4 sine x1. 4 sine x1, 8x2. And again, knowing the locations, knowing what partials with respect to what variables is shown, right, helps me locate these. If you don't set this up, the Jacobian, if you don't set it up correctly, 99% of the time, at least doing it your first couple times, you'll put things in the wrong location in your Jacobian. So I'm just giving you that advance notice or advice. Make sure you identify it so that it's easier for you to place the elements in the Jacobian. So now, easy peasy, x1 equals 0, x2 equals 1. Now I'm going to go ahead and I will build my while loop while the absolute value of f1 of x is greater than, what do you want to put for a number? 1 milli, 1 micro? 1 micro? And, right, f2 of x, because I need both of those to be correct, is greater than 1 micro. And what's my last and? My iteration counter. N is less than, we'll stop it at 10, do your while loop, right? So we'll set N equal to, well, we don't want to set it in here. We've got to set it outside the loop. So we'll set N equal to 0. All right, so now we'll solve for f1 of x is equal to, zoom out just a little bit. So 4x2 sine x1 plus 0.6. That's our first item. Our f2 of x is 4x2 squared minus 4 cosine x1 plus 0.3. So I have my two f of x's. Now I need my Jacobian. So I'll put j of 1, 1, right? We'll just call it row 1, column 1, just to make sure we have it in the right location. That's equal to 4x2 cosine x1, j of 1, 2, 4 sine x1. Try to fix my sign here. J of 2, 1. So now I'm doing my row 2, column 1, which means I'm using my partial of f2 with respect to x1. That's 4 sine x1 And lastly is equal to 8x2. So I've got my 4 Jacobian equations, my 2 f of x equations. That's it. I have all the equations entered in. Now, all I have to do is write my delta x equation, which is the inverse of my Jacobian raised to the -1 times my f of x. I'll just put times instead of parentheses there. And let's just call that of x as well. Update my x. X equals x plus delta x. And then I end my loop. Rinse and repeat, rinse and repeat, rinse and repeat. That's pretty much how you do the first part of the lab. The second part of the lab is to try using nonlinear solvers. I'm not going to be super strict and specific on that. In MATLAB, it's pretty easy to do it. You have a nonlinear solutions where you can specify the algorithm, and you just have to, again, you have to pass it a function name and then some initial conditions, and it should be able to check out. I don't know what your TI-89s do, but I think there are solvers, and then I think it can do nonlinear, but I'm not sure of that. I guess what I'm saying is if you can't get the nonlinear solvers to work on your own, don't worry super duper about it. I'm more interested to see if you can actually do the Newton-Raphson algorithm by hand. Okay. Yes, sir. I'll show you my script file, but basically you have to have what's called a function. I call it an inline function, which is the function where the 2 f of x equations exist. So you're going to be passing it 2 functions that you call f1 and f2. That's what I've done right here. Here are my initial conditions, and then I used fsolve, and I passed it the 2 functions where they live, and then the variables, and it'll just chunk through and do it itself. So you need that, and then the other thing you need is, where's the functions? What's the name? What did I call it? NR function. Why am I not seeing it here? Here it is, right here. So you can see those are just, you call out a function in MATLAB, and you just have to call it out, and then you can see those are the 2 function names that I have. And it'll just keep processing it through. Again, I'm not super expecting you to be able to do this, but it's just a way of checking.
Oh, we want to see part 2 on the line.
If you want to try it, yeah. I mean, again, if you're doing it in MATLAB, it's not a big deal, but if you're doing it on your calculator, I'm not sure how that would work on a TI-89. But you can also try to do it graphically. I don't know how well that works. This is my code. It's only 16 lines plus the 3 lines for the function. It's a pretty simple coding thing. Okay, any questions on the lab? How to do it? Like I said, using the algorithm is actually pretty easy. It's actually starting to write the equations is when it gets more difficult. So I gave you hopefully enough information. So I can zoom out a little more. Hopefully you can see everything you need to be able to tackle the problems. Any questions? Right, I'm going to pause the recording and let you all get to work, but I'm still here. I'll just pause the recording.